Today we want to address a topic that is often surrounded by confusion or misconceptions: quantum entanglement. If you're not sure what it is, don't worry. We'll explain it in the video. However, I'd like to clear up a commonly misunderstood idea right away. You often hear that entanglement proves Einstein was wrong, that relativity is violated, or that faster-than-light communication is possible. None of this is true. Let's explore why. Let's start with a simple explanation of what entanglement is. The word entanglement simply means tied or tangled. But in quantum mechanics, it has a very specific meaning. Two or more particles become connected in such a way that their properties are correlated, even if they are light years apart. The state of one particle cannot be described without considering the entire entangled system of particles. This phenomenon is at the core of many of the mysteries and oddities of quantum mechanics, which challenge our intuition and common sense. To better understand, let's take the example of two electrons. Electrons have a property called spin, which can be thought of as a sort of rotation around an axis, although they don't physically spin on themselves. Spin can only take on two values, +1/2 or 1/5, or, to simplify, we can say that spin can be up or down. It's a bit like a coin that can land on heads or tails. There are no intermediate states. Now we can prepare two electrons in a particular quantum state that entangles them. When we do this, we ensure that the sum of their spins is always zero. This means that if we measure one electron and find it has a spin of +1/2 up, we can be certain that the other electron, wherever it is, will have a spin of 1/2 down. This correlation is already surprising in itself, but this is where quantum mechanics gets even stranger. In classical physics, the correlation between two objects can be easily explained. For instance, if I have two gloves and place one in one box and the other in another, when I open a box and find the right glove, I know for sure that the left glove is in the other box. In quantum mechanics, however, it's not that simple. Until we make a measurement, the spin state of each electron is indeterminate. It's neither up nor down, but in a superposition of states. Only when we measure the electron does the superposition collapse into one of the two possible values. This is one of the most counterintuitive ideas in quantum mechanics. The state of the particle isn't defined until the moment of measurement. And here comes the truly fascinating part. If we take one of the two entangled electrons and send it to Proxima Centauri, the closest star to our solar system, which is about 4.24 light-years away, and we measure the spin of the electron that remains on Earth, the spin of the other electron at Proxima Centauri will be instantly determined, in the opposite direction. This happens at an apparently instantaneous speed, much faster than the speed of light. This instantaneity is what perplexed Einstein, who referred to this phenomenon as spooky action at a distance. To him, it seemed impossible that something could influence another thing at a distance without any communication between the 2 points. However, numerous experiments conducted since the 1970s, known as Bell tests, have confirmed that quantum entanglement is real and that this instantaneous correlation occurs even over immense distances. But, and here's the crucial point, there is no transmission of information faster than the speed of light. The phenomenon is correlated, but we cannot use it to communicate. Why can't we use it to transmit information? Well, imagine you have two friends, Alice and Bob. Alice is on Earth, and Bob is at Proxima Centauri. Each has one of the entangled electrons. When Alice measures her electron and sees that its spin is up, she instantly knows that Bob's electron has spin down. But Bob doesn't know anything until he measures his electron. And when he does, he only sees the result, spin down, without knowing whether that state was determined by Alice's measurement or if it happened naturally. In other words, the results are random, and this prevents any form of communication. So, even though the phenomenon appears to happen instantaneously, we cannot control the measurement outcome or use it to send messages or information. It's a bit like the glove example. Knowing instantly which glove you've found doesn't mean the gloves communicated with each other. Additionally, it's important to emphasize that while entanglement seems to challenge our classical understanding of space and time, it does not violate any laws of physics. Einstein's theory of relativity remains valid. There is no violation of the speed of light as a limit for information transmission. Even though entangled particles seem to talk instantly, no useful information is transferred faster than the speed of light. So, the next time you hear entanglement being cited as proof of telepathic communication, time travel, or other esoteric theories, you can be certain that it's pure fantasy. Even the most advanced entangled systems cannot be used for communication in this way. Moreover, maintaining entanglement is an incredible challenge. The quantum world is extremely fragile. If a particle interacts with its environment, it can lose its entanglement. This phenomenon is known as quantum decoherence, and it represents one of the biggest obstacles in the development of technologies like quantum computers. In conclusion, entanglement is one of the most extraordinary phenomena of quantum physics, but it doesn't involve any violation of the laws of relativity. The quantum world is complex, fascinating, and full of surprises, but the speed of light remains an unbreakable limit for information transmission. We hope you enjoyed the video, subscribe to the channel, and hit the bell to stay updated.